Okay, so what we're going to do now is we're going to move on to module 2. So really the modules are just a way for me to have some context to discuss things that we need to cover. So the core things that we need to cover are to get you up to speed with some basic statistical knowledge, but that's kind of a boring topic, so we're trying to make it a little bit less boring. I won't say necessarily interesting, but less boring by fleshing out the concepts on some themes. So we're going to move on to energy and pollution kind of topics. But before I do that, so what have we actually done? So we've looked at biodiversity for the last 3 weeks, and I hope you've learned a few things that you may not have known in the past. In terms of the statistical stuff that we've been trying to cover, so we've had t-tests is really where we've got up to, so I've just sort of introduced that, and Marit's given you some examples as well to follow on from the things that I've covered. And sort of introducing this framework for processing things, which is a framework that I like, and because I like it's the one that I subject you to, which is that we first create a picture. Whenever we have some data, we like to create a picture. So we do that. In the case of single samples, a histogram is okay. Horizontal box plots are actually also quite okay. Then we formalize our null and alternate hypothesis. So we like to have these formal tests of what we're doing. We have some decision rules to understand our tests, and part of introducing those decision rules is to set alpha. So an alpha plays a role in our p-value decision criteria, so that's something. And then we base our decision to reject the null or do not reject the null. So that awkward language is something that we have to get our head around. There's a very good reason for it. You just have to get in the habit of saying reject the null, do not reject the null. That's it. And then for us, if we're interested in science or natural resource management or any of the things, so by trade I'm an economist, but I still use the same methods that were developed in science to progress things of interest. Okay, so what are we doing? Couple of things that we need to be aware of. We're interested in population values, but we can't ever really get a handle on the population, so we take samples. So when we take a sample, we can use that sample to give us an estimate of the population mean and the population standard deviation. And we saw some scenarios where the quality of our guess about the population mean and the population standard deviation depends on the sample size. Now, we've also introduced some propositions without formally testing these. So the core propositions that I introduced to you were that if you take samples from a normal distribution and calculate the mean, so the distribution of the sample means follows a normal distribution. That's kind of intuitively, there's nothing, no mental gymnastics involved in that one. The second one was a little bit more tricky, which was to say that if we take samples from any shape of distribution and calculate the mean from each sample from that wacky distribution, then the distribution of sample means also approximates a normal distribution. And that approximation gets very, very good as soon as we have reasonably large samples. And by that, I mean, there's no hard or fast rule on this, but in the ballpark of 30 is fine. The other proposition that I had for you was that the distribution of sample means that shape is much tighter than the distribution of the population. And there's actually a mapping rule for the distribution of the sample mean. So we say the standard error of the mean for that, and it is the standard deviation of the population divided by the square root of the sample size. So we looked at some simulations of this. So this is just a screenshot of that. So we're saying if we took samples from a normal population and we calculated the mean for each population and we repeatedly did that exercise over time, the distribution of plotting the mean of each sample would look like a normal distribution, and the shape would be much tighter than the population. We then looked at some more simulations around something that was very much not normal, and in terms of this theorem, this is the most challenging shape for it to work with. Highly skewed distributions are the ones that really push this limit. So we picked the absolute extreme challenge for this theorem and said, look, we're taking samples of size around 30, and the distribution of sample means is starting to look very much like a normal distribution. And there are some really, when we know the theoretical distributions, we can actually map these things in theory. So you can see on the theoretical propositions for my population distribution, when I'm taking samples of 30 from this highly skewed distribution, the distribution of sample means looks pretty much like a normal distribution. So that's because we know this, in this case, we know the population values, it's possible to map these theory things out. So a recap, so I guess I'm going over this because these are really the fundamental things that you need to know about. We always have an idea of the shape of the distribution of sample means. What does that mean? We always know that this thing is approximately normally distributed. So we have a sample mean. A sample mean is a summary statistic, and we have a special language. So we say that the distribution of sampling of statistics are called sampling distributions. And just to make things difficult, we say that the standard deviation of a sampled statistic is the standard error. So we use the standard error of the mean to conduct our tests. So we don't rely on the population distribution looking anything like a normal distribution. We rely on the distribution of sample means looking like a normal distribution, and we know that that's the case. How do we use these propositions? So the example I used was my capital for coal mining example, where I said, look, this company wants to get out there, make some money with a coal mine. You have to do lots of things for a coal mine. You have to build some infrastructure, like some rail infrastructure, but you also have to move the dirt to get to the coal. And so I said, look, this company had gone to the ASX and it was out there, and some people don't want this mine to go ahead. Some people want to make some money, and that's fine. But we wanted to test the claim, and the claim was that we'd have to move 50 meters of dirt before we got to the coal that we could sell and start making money. So that was the claim we wanted to test, and we wanted to know a scientific process that we could test that claim. So the first step in our scientific process, although it's not formal, it's a really integral part of making the convincing argument. So a convincing argument in science will usually involve text, tables of numbers, and figures. They're the three tools that we have to work with. We want effective diagrams, we want effective tables, and we want effective text. So I guess my gig is mainly around the tables and the figures, but we will also be doing the text, because you can't just have tables and figures and statistics. We have to convince people of what we're doing. So we're going to have a null and an alternate hypothesis. We can use some notation. I'm introducing some notation. HO, that's my null hypothesis. Mu0, that's my mean, my population mean. So the population mean is 50. The population mean is not 50 as my alternate. I'll probably use words most of the time, but just introducing some notation. I control what I call the type 1 error rate by using this idea of alpha as 0.05. We need to know about alpha as 0.05 mainly because it informs our decision rule for whether we decide to reject the null or not reject the null. And then we're going to implement the test. So we know how to do this in R, very powerful statistical software. And it's just the command t-test and the things that we want to test, or whether we want what we want to test, and we're going to reach a conclusion. And really for us, the most important step is always step 6, to translate a statistical test into something meaningful. So let's have a look at what we can do here. So here's the distribution of the samples. So they, when they put their prospectus out, they came up with a grid. They had a fixed grid, and they sampled the distance to the coal body, and then they recorded those measurements. Now, we look at that shape, and for me, that shape is probably not normal. I see it running off in one direction. It's skewed. So there are some bits where the coal body is quite a bit deeper than other bits, but there are also some bits where the coal body is quite close to the surface. So we know that the sample mean is 52 and the sample standard deviation is 24. So what we know is that we can use those values, the sample values, and we have some mapping rules to map that to the distribution of the sample mean. And then because we know that the shape of the distribution of sample mean is approximately normal, then we can apply our statistical test. So how do we, we're quite keen to find out whether these guys are scamming people for their money, for their IPO or not. So we implement the t-test. So we read the data into R. We look at, then we say with the data that we read into R, conduct a t-test, and we want to test against a null hypothesis of 50. We do that. We look at the results. The results come out. The t-value is close to 0. So a t-value close to 0 is not strong evidence against the null. We formalize our ideas by looking at the p-value. The p-value is above 0.05, therefore we do not reject the null. All right, and then Marit gave you an example where she was looking at the area of forest. Okay, so some definition of forest. We wanted to have some understanding of this. We want to test a claim, a specific claim. So we're testing against a known value. So we need this single sample t-test. Same steps that we've seen before. Okay, we're going to create a plot, specify a null. So we're going to specify the null in words here. The mean is equal to 40. The alternate, the mean is not equal to 40. Implement the test just like we know, make a decision, and then say something about it. So the plot for this one was pretty informative, I thought. So we saw that the sample mean was 32. There's quite a bit of variability in these measurements. The hypothesis value that we're looking at is 40. So we want to know, is 32 statistically different from 40? Okay, and we've got quite a few measurements. So we run our t-test. So with the forest data, apply the t-test, the column, so the variable name. So we've heard about the data matrix and what we look at. So we're looking at the variable share, and we want to test whether the share is equal to 50. We look at the t-test. We just can quickly look at the p-value. The p-value is less than 0.05, so we reject the null. So we're starting to see this idea that how we conduct t-tests, why they're valuable. They're valuable because they give us the grounds to test the validity of claims. So you hear these things about fake news and crazy things that are going on. Well, we're in the objective science space. We're careful scientists, and we have some tools that allow us to test claims and make sensible statements. And that's a good time for a break.